The equilibrium constant is very important, since once we know the numerical value of a chemical reaction, the direction and the extent of a reaction can be predicted. Let's start with how Kc helps in determining the direction of a chemical reaction. The direction of a reaction at any particular moment can be predicted by inserting the concentration of the reactants and the product at that particular moment in the equilibrium expression. Let's consider the reaction between hydrogen gas and iodine gas. In this reaction, 1 mole of hydrogen gas combines with 1 mole of iodine gas to form 2 moles of hydrogen iodide. The value of Kc is 57 at 700 Kelvin temperature. If we withdraw the samples from the reaction at any particular time, we can determine the concentrations of hydrogen iodine and hydrogen iodide. Let's assume the concentrations of the mixture's components as shown. As you can see, the concentration of hydrogen is 0.1 mole per decimeter cube. The concentration of iodine is 0.2 mole per decimeter cube, and the concentration of hydrogen iodide is 0.4 mole per decimeter cube. The subscript T next to the concentration symbol means that the concentrations are measured at time t during the reaction. This is not usually at equilibrium. If we put these concentrations into the equilibrium constant expression, we obtain a value called the reaction quotient Qc. Qc is the measure of the relative amounts of products and the reactants present in a reaction at a given time. The reaction quotient for this reaction is calculated in the same way as you would calculate for Kc. In this equation on the screen, Qc is equal to the square of the concentration of hydrogen iodide divided by the product of the concentration of hydrogen and iodine. Remember to place T in the subscript of all the concentrations. Take a look at the formula. It should look similar to the Kc formula. The only difference is that the Kc value is at equilibrium, while the Qc value is at any time other than equilibrium. Understand? Great. If we insert these values into the Qc expression, we should get the square of 0.4 divided by the product of 0.1 and 0.2. By solving this, we'll get 8 as the value of Qc. Now, to be able to predict the direction, we must compare the value of Kc and Qc. As the numerical value of Qc is 8, which is less than Kc, which is 57, the reaction will not be at equilibrium. Qc requires a larger concentration of product to achieve the equilibrium value of 57. So, this reaction moves from left to right in a forward direction to attain equilibrium. As you can see, the reaction quotient Qc is useful because it can predict the direction of the reaction by comparing the value of Qc and Kc. We can now make a generalization about the direction of the reaction. There are 3 possible outcomes in this situation. If Kc is greater than Qc, then the reaction goes from left to right. In other words, it moves in a forward direction to attain equilibrium. In the second case, if Qc is greater than Kc, the reaction goes from right to left. In other words, it heads in the reverse direction to attain equilibrium. Lastly, if Qc is equal to Kc, the reactions take place at an equal rate. In other words, equilibrium has been attained. Make sure to revise these concepts so that you may be able to predict the direction of the reaction.